Good afternoon. I invite you for the next lecture from Computer Architectures course. And our today topic is education kit, which we have built to allow you to take your hands on some peripherals and hardware on a small embedded system. We call that system B35APO to inform that it is based on some micro Z board and it is intended for the APO course. Okay, so the outline of today's lecture is that we start with the description of this hardware, and then we continue with some information about memory map peripherals and how to output the text on the display. And then I can present you some of our projects which we built on this hardware for real application or for more advanced diploma thesis and so on. So we can continue. So the kit which you will use is the small embedded system. It is enclosed in the plexiglass enclosure, and it is for each computer system you need some power supply. So you will get a 19 volts DC power supply, same as for some laptops. It is connected here to the kit. Then the kit can communicate with external world through the USB and Ethernet communication. And for the peripherals where you can implement your semestral project, there is the small display. And then there are 3 rotary knobs to input some value. You can copy this value to RGB LEDs and so on. So basically, you have some small system. It is without the touch screen because our idea was that touch screen would not survive so many students in the years which would work with the kit. So if we open and take away the display, then we can see that there is a single computer module which is bought, which is based on the Xilinx Zinc chip, and then we have there some peripherals, those knobs which allows to tune the input value, 24-bit, for example, color or position on the screen and so on. Then we have there set to LEDs which are directly mapped into the address space, so you can change the individual LEDs. Basically, if you write the 32-bit word into some address, then you can lit on and off some LEDs. We have there possibility to work with some simple microphone. We have there a speaker. It is possible to connect PS2 keyboard. We have there the option to connect RC servos for the RC controlled models, so up to 4. There are the connectors which allow to connect 2 parallel cameras. One of my bachelor thesis students is now working on the stereo image processing from those cameras in the programmable logic. And the actual board has the small micro USB connector to connect the console, but to ensure that it survives for a longer time, we have decided that it is remapped by the reconfiguration through the bootloader and Linux kernel to USB-B connector AB, which should be a B in the fact, which ensures that it is more durable and survives longer. There is a reset button, so if you press the reset button, then board starts to boot from the network. In our case, we have some kits which can be lent for 1 week to the team, and then we have there 18 boards which are for the work during the seminaries. Okay, there is possibility to connect to peripherals to programmable logic with PMOD standard, and it is possible to connect there even some peripherals which are intended for Altera chips and development kits. If we zoom in, if you look at the actual single board computer or system on module, how it is called, then we have there some block of the power supplies. So we provide 5 volts from that 19 volts to this module, and it prepares 1 and 1.2 and 1.8 volts and other voltages which are necessary for the actual chip. Then we have there the actual core chip, system on chip with FPGA part. We have there that Ethernet. On the bottom side there is the SD card. It is possible to boot from the internal flash or from the flash on the board or from that SD card. SD card has advantage that if there is some problem you can swap it and so on. So we boot bootloader from SD card and the rest over the Ethernet. There it is possible to select which boot option we will use. There is that important reset button which allows to reset the board to the initial state. One button which can be pressed and checked by the user. There is some debug access port. Some peripherals are available on this PMOD connector. Disadvantage of this connector is that it is not connected to the internal FPGA logic. It is connected to some peripherals. There is some SDRAM chips and so on. And this is bottom view. So there is micro SD card and 2 108-pin connectors which connects this module with the rest of the system. And the module is evaluation kit from the Avnet. It is originally based on the project of Z-board community, and it price is something about $200, and it is system on module or single board computer. Actual chip costs something like 90 USD. There are bigger chips. This is the smallest one and cheapest. But today you can buy, for example, Versal systems, which has something like 100 multiply 10 9 transistors on the chip. So it is quite massive chips, but their price is extremely high. And this is maybe a future of the neural and special computing and so on, because this is the reason why AMD has bought the Xilinx company. They integrate it into their products because for some specific workloads and complex data processing, you can have a problem to implement it in the software. You can implement it through some vector extension and so on. It is still not fast enough. Then you can add some neural network MPU accelerators or graphic accelerators for the faster computation. But even if this is not enough, then you can use this programmable logic where you have multiple network, neural network accelerators, digital signal processors, some ARM cores, and you can connect it according to actual needs of your workload. It is much more complex than to program something in a cloud with a standard ARM or x86 architecture, but if you need a throughput, then this can be an option. So this is the important that this chip has not only that, in this case, two relatively slow processor cores, but it has even that configurable logic. The chip is based on the dual-core ARM Cortex-A9 processor. It has some small, fast static memory tightly coupled with the cores. And what is important, there is that programmable logic, which provides about 4,000 slices, where each of those slices is small configurable logic circuit. So basically, that circuits which you have seen, that gates and or some flip-flops and so on, which was at the start of our course of our lectures. So basically, you have this option, and each of those slices can implement up to 8 flip-flops, so the bit memory for single bit, and 4 logic functions, where each of those logic functions can process up to 6 inputs. And at the end, if you multiply it and so on, it is about 28,000 of logic blocks, which is equivalent of 430,000 of equivalent logic gates. Those are those 2 input gates as AND, NAND, and so on. If you consider that in 90s, you can buy a small DIP package with 14 pins usually, about this size, which implements 4 gates, for example, 4 NAND gates. Then, in the fact, you get into your hands the stack with 100,000 of those chips. And you can decide how to interconnect them internally at boot time or even runtime. So you can implement, for example, your own processor. So some of my students has implemented theirs, the coprocessor for sure. If you implement coprocessor in the configurable logic, then it is slower than if it is directly etched into the chip onto the silicon. But you can add special functions and so on, so it quite often helps. There is some amount of distributed memory inside of this chip, so it is organized as 36-bit wide, but it can be reconfigured even to different sizes, and it is fast, and it is with double input-output ports and so on, dual ports, so it allows to implement some interesting functionality, caches and so on. There is 80 DSP blocks which can multiply to 18-bit integer inputs with 36 output bits, and it can be sum added together to 48-bit accumulator, and you have 80 of such blocks inside the chip, so you can combine them and build a pipeline specific for some specific processing. And on board, on that system on module, there is 1 GB of external DDR3 memory, 1 gigabit Ethernet, micro SD card, which allows to load U-bootloader in our case, which starts the Linux kernel and the operating system over Ethernet. So it has advantage that even if you get the full root access to the board, then if you do something which breaks the system, then you can reboot it and it starts from the initial state. For sure, you need to be careful that no data are stored there if you reboot it, so you lose all the contents of the memory. Okay, because the network file system is mounted in read-only mode, and there is only a difference kept inside the RAM. There is USB host connector, so you can connect even some cameras on USB or some another joystick and so on. And there is USB UART as a console that you can again connect through the USB to the computer and monitor what happens. There is some small Quads SPI connected flash, but we do not use it at this moment. So it can boot even on its own without the SD card and so on. And this is the actual chip, or chip. It is in the fact the integrated circuit, and inside is somewhere the chip. And for those high integrated circuits, you need quite a lot of the pins to connect to the board. So it is usually soldered through fine pitch ball grid array. So there are small balls of the tin which are somehow stick on the conductive pads, and when you place the chip with the balls onto the PCB, printed circuit board, with soldering path and so on, then if you do a reflow heating, then it is correctly soldered, that ball melts and it is connected. There is, from my colleague, such joke that you can even try to connect it wire by wire, which is quite hard, but yes, somebody has made it. It is problem that if you have already used chip or used chip or this component, then you need so-called reball it. So basically strip away the remains of the soldering and rebuild new small balls, and it is not so easy. But one of my colleagues has succeeded with graphic chip to solder it this way in his hot air oven at home. So sometimes there are options, yes?
Where did he get the stencil for applying the balls and the paste?
Okay, if you want to solder it on the board, then there is one technology step when there is dispenser which puts the small drops of the paste. Yes, and if you strip it away, then if you want to reball it, then basically you need to clean the pads and then put there a small amount, or ideally dispense there with the dispenser, ideally robotic or something which dispense exact amount on each of those pads. And if you heat it, then the balls appear. So in theory it is very easy. In practice it is not so easy.
Also done it on a really small chip, like not with so many pins, but it's not an easy job. And
it is possible to try. And okay, if you have interest to do some real hardware design here, we have LVR laboratory in Davice, where they have all this technology. So basically, a professional, not the hot air oven for the kitchen, but real stuff and microscopes and even the X-ray imaging, so you can check that it is correct. Okay, it is not for the mass production, but it is for the experiment, it is enough. Okay, so now we go down to our chip. So if we go into our chip, we can see that there is the system on chip logic, so-called processing system, which has two Cortex-A9 cores with floating point and so on, and those are connected through the AMBA, Advanced Microcontroller Bus Architecture interconnection, to some fixed peripherals. So for example, you can find there two serial ports, some GPIO input outputs, SD card connection, USB. In the theory, there are 2 gigabit Ethernets, but only one is connected on the board. And then there is some static memory and controller of the dynamic memory outside of the chip. So this is relatively low performance computer from today's point of view. But what is interesting that there is that another part, which is so-called programmable logic, where you can implement your own hardware, so basically logical design by configuration of those cells. And it can have even PCI Express connection on those little bigger chips. This which we use is only the version 10 at the end, and it doesn't have PCI Express. But we have some even bigger chips there for the diplomatics and so on. Okay, there is some analog to digital converter and so on. If we go down to those parts which you already should know from our previous lectures, then we see that there is the actual, or there are 2 in the fact processor cores, one and the second. They have, in addition, the coprocessor for the floating point computation. So if you remember to the lecture 2, then those operations are possible, and not only a single, but even 2 single precision floating point operation can be done in the parallel, and even the instruction for some more complex operations are there. Then we have there some debugging facilities. Then there is L1 cache, which is on the separate for each core. And then there is a shared L2 level cache for the both cores and other peripherals. There is some unit which allows to ensure that we provide a memory coherence between the cores and so on. It is, we will notice it and have some simple introduction in one of the following lectures about those problems. Okay, static memory, it is simple. Then we have the direct memory access, which allows to copy data directly from the memory to the peripheral or vice versa without the need of processor to take care about each word and so on. If we look at the consumer devices with this core, then you can find it in the Apple A5, for sure not with the FPGA. It is some another chip, but it is similar, or in some such Asus Transformer pads, or in NVIDIA Tegra 2 and so on. It is 32-bit, so from the point of view of today, high performance processor in the mobiles, it is not so fast. But anyway, we can go again to the microarchitecture, and there you should be able to recognize at least some basic blocks which we have in our pipeline processor design, and then we started our superscalar design. Again, this is very simple processor from the today point of view, but anyway, it has some cache for the instructions. Then there is some mechanism to feed fast loops to the rest of the core. Branch predictor with global history and branch target buffer and return stack, so something which we have seen during the 6th lecture. If we fetch a correct instruction, then they can be decoded two in parallel and go to the register rename stage, which assign to the architecture registers the physical registers, which allows to resolve write after write and write after read hazard. Read after write has to be resolved by some forwarding or stalling and so on. So we can decode the instruction up to 3+1 instruction can be dispatched in the single clock cycle. And we have there this is the rename. Then we have issue, where we send the instruction to the actual execution unit. And we have there two arithmetic logic units which multiplication support, two without multiplication support. Then we have that floating point and neon, which is the multimedia extension, and address generator. And then there is a write back stage, which ensures that the actual effect of those instructions on the memory is reordered to the original order. So it is in the factory order buffer. If we access a data, then there is some automatic prefetcher which allows to estimate new next access to the memory and prefetch data in advance. Then there is load store unit. It has some store buffers which keeps the data when the another data are read into the cache and keep the data that they are later stored to the memory. Data cache, we need a memory management unit to have a virtual address space for the processes which are mapped to the physical one. And at the moment when we have a memory management unit, we need a cache of the translation. So there is that micro TLB. And then there is some tracing of the for the tracing and ability to debug the state of the core. And the two cores are connected to the L2 cache, and there is some master and secondary master interfaces which go to the rest of the chip. The actual architecture is little endian 32-bit RISC ARM. Okay, it should be okay. RISC. I have written RISC little endian, but it is ARM. Yes, we have 16 general purpose registers, and even that the processor runs typically at 800 and something megahertz. Then thanks to the ability to decode two instructions in parallel and ability to combine addition together with following multiplication and so on, it can achieve up to 2.5 DMIPS, which is Drystone synthetic computation benchmark for the computation of the integer processing capabilities of the processor. And at the end, we get to something like equivalent of 2,000 of mega instruction per second, plus minus. What is important that for the simple integer operations as addition and so on, we get the latency of single cycles. So next instruction can use the result of the previous one directly in the next cycle. At the case of the multiplication, we need 4 to 5 cycles. For the floating point operation, we need already 4 cycles for addition and subtractions, 5 cycles for multiplication. Integer divide is not written here any at all, but for the floating point we need 15 cycles, and if you want to compute a square root, then you need 17 cycles. On the other hand, if you want to implement some game in 3D space, then you probably know that the second root square is very important because it allows you to compute distance and scaling and so on. Which is interesting that, for example, maybe who knows a Doom game? It is somebody at least knows it. They have done a very clever trick at that time how to estimate with not so high precision the second square root, which helped their game engine to provide a good throughput and ability to work with 3D on relatively slow computers. By the way, one of our students has ported to our kit open source version of Doom, but yeah. Okay, we have branch predictor. It has 4,000 2-bit predictors in branch history table, which is something standard, and we have a memory management unit with 2-level page table. And if we look into the caches to match with your knowledge from the lecture, I think 4, then the capacity of L1 is 32 kilobytes, which is similar even to the x86 chips. It is 4-way associative and separate for the instruction and for the data. So we have 2 caches in the fact there for each core, and 2 cores, so 4 blocks at all. Block size is 32 bytes, but the replacement policy is pseudo-random or pseudo-round robin, which is not great because you sometimes replace the row which can be used in the next operation and so on. So it is not optimum. The cache provides write back or write through allocate and non-allocate policy, so we can use those variants. And L2 cache is connected to some coprocessor. I have helped with this support to RTMS project on this chip. It is a little interesting how you access and command this cache, because cache is in the theory, doesn't need any maintenance. But at the moment when you have there some peripherals and you need to ensure the data are already in the main memory, that peripherals see those data and so on, then you find that even that simple rule that cache is of no care for the programmer is false. And it has 512 kilobytes. It is 8-way. Row size is 32 bytes, which is better if those match. If those do not match, then it can result in the surprising result. It needs more care about operating system. It has pseudo-random replacement policy, so again, this is not so good. And support write back, so basically updates only in the cache, and when there is a need for the new data, then you write back modify data to the memory or write through. And you can control which part of the address space, virtual address space, is cached and which not by memory management unit. And for the paging, we can return back to the Intel. So in the Intel case of 32-bit Intel architecture, we see that we take the 10 bits, have for each process, we have page directory base register, add offset or index multiplied by 4, we get the entry, we get to the base of the second level of the page table, again at the index formed by next 10 bits, and we get the base address to the page in the physical memory. Again, to highlight for you, those data structures in the fact, those page tables and so on, are in the fact not a separate memory, but again are allocated somewhere in the main memory. So the rule that the segment of 1024 entries of 4 bytes takes the 4 kilobytes, and this is agreed that it has the same size as the page. For the case of ARM, there is a difference. They decide that you need a 16 kilobyte page directory. You use 12 bits to index into this. It combined with the actual address space base directory. Then you get to the next level, and this one is used to index only by 8 bits, so it has a size of 1/4 of the page, because page size is in this case same. The 12-bit 4K pages are very common, except for the Apple M1, which has 16K pages, but it can be switched even to into the 4K mode. Okay. So, and now we go to our peripherals. So you should remember to the previous lecture, and there are again no specific input-output instruction on the ARM architecture. So you need a standard load store instruction to access memory and peripherals, and they differ only by the address. So basically you decide that some area in the address space is used for the peripherals. It can be even mixed, that there is, for example, some part for peripherals, some parts for the memory. Usually the memory is continuous and so on. And if we speak about the FPGAs and those systems on chip, then they usually do not have bidirectional data bus or even multiplexed address data bus as we have seen on the PCI. But in this case, we have usually separate output for the address. Then we have separate output for the data, which are, according to the address decoder decision, routed to the RAM, or they are routed to some registers in the peripheral. In the case that we want to read, then we do not activate a write memory signal. We activate usually some read signal, but it is not necessary in this simple model, because in this case we switch which device or which memory we want to read, and we have the inputs to the CPU for the data. And if we look to the actual implementation of this advanced microcontroller bus architecture, which is the ARM development and standard interface, which you find in your mobile phones and so on, then it is a basic, and we use there Axis 3 or Axis 4 version, which is advanced extensible interface. And if you want to connect a simple peripheral, so basically there is, for example, a CPU, and it wants to communicate with, for example, that line of 32-bit Z2 LEDs, or read something from the knobs and so on, then you need to connect those 5 channels. You have separate channels that there can be run in parallel read operation and write operation, for example, from the other core. And even each of those buses or those direction is divided to the channels. So basically what we need to send is to send address, what we want to read, and then we start to receive a data for those for this address and the following one and so on. And the master interface or initiator interface informs if the next cycle should be the final cycle, so we can stop the reading. For the write, we need even 3 channels, because in this case we send address. When the device is ready, then there is a transaction when the address is delivered to the device. In parallel, or a little later, we can negotiate the data words can be transferred over the those links, and when there is a final write operation, then write response goes in the another direction, which confirms that the data has been written correctly. No. Okay, like, very like. But it is not UDP. It is network. It has, okay, it is not directly a packet protocol. If we start to speak about a PCI Express, then it is really packet protocol on full duplex link. In this case, we will go a little deeper, so you have some idea how it looks like, and if I have some time, I can show you the how we can connect those peripherals in the design tools and so on. So if we go to the actual wires and want to implement read transactions, then we need those two channels, one for address for read, and the second for read data. So this is AR is address for read operation, and for all those channels there is the rule: when the initiator is ready to provide, when the source of the information is ready with the information, for example, there is a valid address, then it informs, okay, address is valid. But the transaction is considered complete if at the given racing clock edge there is an address ready, initiated, asserted by the target of the operation. And at that moment we consider, okay, address is ready. In the fact, we can try to assert a new address even before the data are returned, but usually it will result in the not ready by the target, which informs that it is ready only somewhere later. But in theory, there can be a queue of the requests to different addresses, and for each of those requests, there is a stream of the data words coming in the another direction. And again, in this case, the receive channel receiver, so basically in this case the CPU, for example, or the master, informs, I am ready to receive data. And at the moment when the peripheral informs, okay, the data are valid, then at the clock cycle, at the racing edge of the clock signal, there is realized the transfer. If there is not ready, then given data are not considered valid, and we consider valid the data when there is already the receiver of the data, but source has some problems, needs to delay, wait, for example, for the memory and so on. So basically there is that rule that on each of those channels we have the valid and ready, and if both are asserted at a given rising clock edge, then we know that the transfer has appeared, and we consider it as the finish. And okay, no, and there is already, and this is the last. This is the last. So basically, if you want to read only the single word, then you assert the last directly here, and you know that this data transfer is the last one, and then the next transaction start. So it is implemented this way, which allows relatively quickly respond, and respond even with the burst to some DMAs or some fast peripherals and so on. For the write, it is a little more complex, because in this case, the initiator, for example, CPU, needs assert the valid address. It needs to wait that the address is accepted by the second side. Then it can be run in parallel, but usually we can assert the valid and ready only when the address is known, because before we do not get write ready signal. And then we can start to write the data, and for the last data word we assert the write last, and it informs that after this clock cycle bus is considered as finished write transaction, and we get back on the B channel the information that the operation has been finished correctly. So this is the option what we can use. And if you want to design such system, then you can see that basically we need to work with something like read channel, address, and data, write channel, address, and data. So it is 4 times 32 wires, plus each of those channels needs something like 7 to 10 additional control signals. So if you want to do a design, then it is relatively hard to implement it and to route each wire. So there is a tool, Vivedo system, which allows to connect those peripherals and IP cores, so basically design blocks, together by a single link, which corresponds to the whole bus, and it automatically maps it. So, for example, if we go there, I can make it a little bigger, then we can see that this is the AXI general purpose interface 0, and it goes this direction, and we can map it that it goes somewhere there to this block, which takes yes, there's the bus, and it implements even the address decoder. So there are the slave interfaces for the individual peripherals, and for example, if we want to flash with our LEDs, then we need to go to this SPI LEDs and encoders. So basically through this wire, and you connect only this single wire in apostrophe, single signal, and it goes to the connection of all those necessary signals for the peripheral, and this peripheral implements some registers and so on. So we go to that part a little later. Okay, so what you get? So basically, if you want to do something more complex, it is possible to design your own peripherals. There are all tools available on the computers, but it takes relatively long time, because even the compilation synthesis of the design takes something like 20 minutes and so on, and you need to know VHDL or Verilog language and so on. So for your simple task, you have there some peripherals which we have prepared, which are simple, really educational peripherals. So if we look into the physical address space of the kit, then we can find that there is 1 gigabyte of the reserved for the DRAM memory at the start of the physical address space. Then we have there the 1 gigabyte range, which connects to the FPGA. So it is AXI port, where you can implement the peripherals or some subsystem memory and so on. If you try to write to some area which is not responded by the FPGA part, then your processor stucks. So it is necessary to set up this FPGA before you try to access it. And our initial peripheral is that knobs, where you can and LEDs, where you can blink LEDs, same as on the simulator. So today's seminar we start with the simulator, and maybe later we look at the actual hardware, and then for the next seminaries you will work with the hardware. And then the second one peripheral for you of your interest is the LCD display, which is quite simple display, 16-bit color depth. We look at it a little later. Then we have the possibility to connect DC motors with positional feedback, so you can build some control system with this and test it. Then you can connect some ZRC servos or PS2. There is some interface which allows a simple audio output. And then there is the next 1 gigabyte range for the second connection for the second bus to the programmable logic. And then there is reserved some part for which is reserved for the internal peripherals of the chip, and some area where is mapped the internal RAM memory. But we have some problem because we want to use this board with the Linux operating system, which makes the thing simple because you can connect to it, you can load the program even through the SSH, but and then have the output and debugging and all this stuff. But we want to access directly the physical memory, that you get that hands-on on real peripherals. And we have already, I think, mentioned that in the past, that it is possible not only to read and write the memory, but it is possible, or files on in the file system, but it is possible to use even the mapping. It is operation which is possible even on Windows. It is little, only different name is there, but it is possible. But on the Unix system, where we try to keep everything as the device, we can open the file, virtual file, which represents the physical memory. This way we get a file descriptor, and we probably do not want to use a cache. So if we open it this way, then it means, okay, I want to access it without the caching, and for read and write. And now you can use a nmap system call, which provides the information to the kernel that you want to map part of that file, or in this case, a physical address space, to your virtual address space. And you can select at which location, but if you left it at the 0, at null, then it means that the kernel finds some free part of your address space. Then there is the size of that view to the physical, that window to the physical address space. Then you can decide if you want to provide it for the reading or writing only, or for both. Then there is the important thing that you can decide that it should be a private mapping. In this case, each write result in the copy on write operation, and your data do not appear in the hardware. So it is what you probably do not want. So in the shared mode, it is visible to other processes and to the peripherals. Then you need to select that it is this defmem operation, and that we want to operate on this file representation, and the physical address of the first word which you want to access. There is some problem that this address has to be 12-bit aligned. You cannot map half of the page, so it is necessary to do the full mapping. You will get a support function for this operation. So, but it is the principle. And now what you can do, again, exactly the same on the simulator. You can access this block of the peripherals. Only difference between simulator and this hardware is different base address, because there the base address is given by the that window where we can map the peripherals in the FPGA, in the programmable logic, to the physical address space of the processor. So this is limited that it has to start with the from 0x4 to 0x7FFF and so on. And in this case, we have there the first probably this peripheral, this register at the offset 4. And if you write the value there, then you can let on and off the individual LEDs. So you can check that you can access the peripheral. Then you have there two RGB LEDs, which can change color by the 24-bit true color value. And then you have there those rotary knobs, which allows to tune again 24 bits, which can be a color, but binary value can represent, okay, position, what you want. And then we have there those 3 bits, which detect the press of the button, and those are connected to the offset 2.4, and the RGB LED one is at the offset 1.0, and another is at 1.4. And then you have there the LCD display for some simple output. In the typical application on the small chip, small embedded systems, you usually connect it through the parallel or SPI or serial connection. On the bigger system, you usually have ability to map whole video memory to the address space. But due to the requirement of low price, we have chosen the display which has a local controller. It has the advantage that this local controller refreshes the image on the screen again and again, so it is good. But we need to write the data through some interface to the internal memory of this display controller. And in our case, the display controller responds to 2 addresses. On one address, it responds by the writing the commands, on the another address by writing the data. So if we want to write to such controller, then we need to write to some physical address. We start with the virtual address space. According to the mapping and page table, we get to the physical address space, to the AXI bus. AXI bus gets to the peripheral, which we have designed for this purpose, and this peripheral then ensures the correct communication with the chip with the controller on the display. So basically, we have there the in the fact 3 addresses which are usable in the physical address space. So we start at this address 43C0 and all zeros. And at the offset 0, there is a control register which has only 1 bit active, which allows to set a reset condition and reset the chip controller. Then there is at the offset 8, the port where if there is a write, it results in the transaction on the parallel bus, which sends the command to the display. And you need to set up the display, which requires a lot of parameters tuning. We have that code for you. But if you want to start to send data from the upper left corner, then you can send this command to C, which informs, okay, follows data pixels colors, which will be written on the display. And if you write to the offset C, so 12 in decimal, then each write of 16-bit value result in writing of 1 RGB pixel with 565 encoding, so 5 bits for R, 6 bit for green, and 5 bit for blue. Do you have some idea why if we have this asymmetric assignment, because 16 cannot be divided by 3, why we use 6 bit for a green? What is the reason that the green is 6 bit and others are a little less? It has nothing to do with the hardware in the fact, it has something to do with the... Yes. Yeah. Yeah, has high sensitivity in the green color. So basically for this reason, the green is 6-bit in this case. And okay, so it is all for our peripherals. Now we look at the text output on the display. So if you have some font, then we need to define at least some basic properties. So basically, you have some size, which you know if you select the size in some pixels of the font. But above this size, there is a space for the accent marks and other such part of the letter. Then you have some descent for usually for the letters in lowercase, which needs something below the baseline. And then you usually need some spacing between the lines if you want to write multiple lines of the text. And okay, if you have no diacritic, then you can start directly with the description of the font on the that leading line. But okay, so it is for the mathematically or some functional defined characters, but usually for a simple system we work with bitmap fonts. So in the case of bitmap fonts, we need to know which pixels in some matrix should be set and which not, and we map usually those glyphs, as it is called, glyph, to the code through the ASCII character table. So you probably know that 30 hexadecimal is 0 character, for 1 hexadecimal is A, and 6-1 is it is capital and lowercase a, and so on. And usually the second half is specific for a given font, or we can use Unicode encoding where we can have a much larger character set. Okay, so as for the fonts, there is such interesting remark from my colleague who has prepared it. There was a big scalable font war between the TrueType font by Microsoft and which use a different kind of the Bezier curves than the PostScript fonts, which has been designed by Adobe. But later those two ways how to describe mathematically the precise shape of the glyph of the character shape has been designed as the OpenType, and it is used usually today for the vector fonts. But we will focus on the simple case. So basically you need somehow to rasterize those glyphs defined by the Bezier curves to the individual pixels. You can go to the black and white, or if you add anti-aliasing and grayscaling or somehow alpha channel that you can map the characters over the background and use the transparency, then you can get a little better shape. Again, for your case, we expect that you will use that simplest way with directly mapping the pixels of the character to the ones and zeros, and you get the files with this description of the font. So basically, this is only the commentary part, but the actual data are those 16-bit hexadecimal values, and it is organized by 16-bit for some historical reason, because BMP picture format has used 16-bit components, or 16-bit basic unit. And in this case, the character is encoded into those 16 bits as the bitmap, but with a single bit per pixel. So you see there are 0, 0, 0, so this means no activated point, nothing on the screen. But then there is a C1C, which is in the fact in the binary 0, 1, 1, 1. So this is those 3 ones here, and then again 1, 1, and then there are some another zeros, and so on. Is described each character. So you have the glyph, you have the font shape for it, and you will get a multiple of those font shapes which you can use in your simple application. And I have there some real application behind this. It is our fonts are based on the micro windows Nano X implemented by Greg Haer. There is that micro windows framework, which in the fact provides an API similar to the Windows GDI or to the X Windows API. So, but it is very small, so we have been able even to use it on the system which has only, for example, kilobytes, 32 kilobytes or 64 kilobytes of the RAM and something of the flash. So it is the advantage. We have used it even in some bigger applications. So this is example of our actual hardware, which was infusion syringe pump for the hospitals. And this is one of the screens which was there. You can see that we can work even with the Unicode. We have even some Arabian alphabet and some Russian glyphs and so on, so it can be switched to the different modes. So there is an example. We have not used Linux for this one, but due to the certification, we have used RTMS, which is operating system used by European Space Agency and NASA for the flight missions and so on. So, by the way, now is starting Google Summer of Code, so some students are working on this, not on our hardware, this is old legacy, but on some project with RTMS. But it is possible. We have port this system with the graphic even to some small devices. This one has 32 megabytes of RAM, so it was not so small, but even to those 64K systems and so on. And the actual font is described by this descriptor, which starts with the pointer to the name. Okay, you do not need to care about it, but there is a name. Then there is a maximum width of the character. So the character has some maximal width, which is this. Then there is the height of the character. This is constant for all characters. So ascent, so basically how many pixels are for the acutes and so on. Then there is the first character of the font, which is mapped to the glyph. So for example, it can start at 20, 32 decimal, and the characters from encode by 0 to 31 are ignored. Then there is size, how many characters from the first character are mapped to the actual glyph. And then there is the offset to the bits, to that 16-bit entities. And if you do not have the additional information, you can have there the offset, which maps the individual characters covered by the range to the offset to the bitmap. But if you do not have this offset table, then in such case, you can find the glib start by finding how many 16-bit entities are necessary to cover the width of the character, multiply that maxed width, multiplied by the height of the character, and then multiplied by the offset index to the character. And this way you can get to the actual binary data, which informs where you should put pixel and where should be an empty space. If you have the offsets, then you can use offset for this operation, and you can have there even a description of the width of the characters for some of the fonts, which are proportional. So basically, you can write, for example, the I as narrower than the M character and so on, if you have this description. And then there is a default character, which is used to inform what you should print if you do not have the glib for a given code. So it can be some question mark or something to find that there is a problem, that character is missing, and the size of bitmap. So, okay, we can look at some more complex project which we have done on this hardware. The hardware has been designed by my colleague Peter Porazil, that baseboard, the actual SBC, that single board computer is bought, and I have led his work at my company, and it was on the requirement of my former head at the department that I should provide those hardware for the education. Okay, the whole sources of the mechanical design and the PCB designs are available for that development or educational kit, not for the SBC. For this are only schematic diagram and documentation, because it is bought from Avnet. The actual PCB design has been done in our own software for the PCB design to overcome problems with and do not care about some commercial stuff. But today you have there probably KiCad, which is much better. So, Altium is, but you do not get it for free.
Unless you're a student.
For some time and with some limitation. So you have KiCad, I think, and it is a better option. But when we have a problem to find some cheap, reasonable stuff for our company, we have decided to write it. And it works. So it is possible. You do not need to be afraid, basically. It is possible. But today, KiCad is used by CERN and so on. Okay. The FPGA design of peripherals has been done by me and my student, who has worked on the CAN bus project on this hardware. And you can get even not only this design for the for our subject, for APO, but even other designs which we have in this repository. And the actual kernel is quite old, which is running at this moment on the board, but it is a fully preemptive kernel variant. So it has very nice real-time properties. And on the other hand, we are running a daily build of the kernels for some latency testing. So we have even, if somebody wants, it is possible even to run the actual yesterday kernel, because it is built on some of our servers and tested on the hardware. But for this, we have this older one. I want to update it when I have a time. There are some build instruction and there is some documentation. This is for the Czech course, but there is a link to the English variant, and you can find this hardware user guide from Avnet. And for example, what we have done, we have our own MATLAB Simulink target, which allows real-time control, and you can build a whole complex control application in the graphical environment and run it on the hardware. So I have shown this already in 2017 and so on, so we have this for a long time. There is our variant of the target for the MATLAB Simulink, but you need to buy MATLAB Simulink for sure, or at our university you have it as a campus license. But we have there some alternative. For example, this is our robotic library, which is used in many applications, which runs even the robotic controllers on the Chirk in the Davice for the students for something like 20 years, but we have even actual ports to some small FPGAs and so on. You can find some presentation problem is that those has a recording in Czech, but you can find some of them there. But usually thesis and so on are in English, and presentation slides are in English as well. This is our cabinet with two of those boards and the 64-bit testbed controller, which is able to reboot the boards and so on, and running a daily test of the standard and fully preemptive real-time Linux kernel. So we communicate with the community and we are trying to debug some problems and so on. So we have those tests running for already it starts the third year. You can use even that DC motors kits, which are available there in the shop. So you can use those to basically control the motor. If you have DC motor, then basically you can connect both its end to the ground, then it is stopped, or you want to connect one to the ground and one to the power supply, so this way. And if you alter the state when the motor is connected to the power supply and when it is connected to the ground, to the low level, then you can do a proportional control of the voltage which is connected to the motor, so pulse with modulation. If it is fast enough, then the integrative character of the motors filters the current, so basically it is almost steady, and our peripheral allows to enable motor, then it allows to select a pulse width modulation duty cycle, so it means how much of the period is filled by the logic high level, and select the direction if it should be applied to the one on another end of the motor, or another terminal of the motor. So this way it is one direction, this way you get another direction, and you can select here a period of the pulse width modulation. So basically all parameters, and there is a quadrature encoder. So if you have on the motor the incremental rotary sensor, then you can get the position directly from another register. Or you can do something, okay, so this is the example how you can control it. In this case, not from MATLAB Simulink, but from the PySimcoder system, on which we cooperate with Roberto Baccer, professor from Switzerland. And okay, it works quite well. So for the simple education, you do not need to pay anything. You can use this relatively expensive kit, but it runs even on the cheap kits and STM and Raspberry Pi Pico and so on. So, okay, and it is all for this basic presentation about the hardware which you will have for your semestral projects. So if we want to see how LCD display works, then basically it is based on the light polarization and the filters, which allows only one direction of the polarization to go through. So basically, if you have those lattices and you can somehow tune them, then in such case you can for a given pixel define if it is seen or not seen, if there is a light intensity and so on or not. And this is one option, if you can change the orientation of this filter. But if you use liquid crystals, then they have such interesting features that at the moment, when you organize them with the electricity, that they start to turn the polarization polarization of the light, and this way you can decide how much you want to tune it. And if you have a polarization filter on bottom and top, then you can control how much of the light goes, for example, from the backlight to the screen output. And if you add there the filters for the individual colors, then you can have RGB display. Today you can switch sometimes even to the LEDs, that the actual component here is Slayer emitting diode in each of the pixels, but LCDs are typically implemented this way. And you can have a transmissive which needs a backlight and control how much of backlight goes through which pixel. You can have reflective which has only one polarizer, and then you go down and up through the same polarizer over the reflective mirror. Or you can have translective, which are great, that are well seen even on the daylight, but even in the night when you can use a backlight. But usually this technology has problems that the colors are not so, are a little dimmed, so it is a little problem. So usually we have this kind of the displays. And the actual display can be a passive matrix, which is much more complex to describe, or it can work exactly on the same principle as the memory. So basically you select the, in this case it is not word line, but in this case it is a row line, and then you can, if you switch those transistors on, write send or set up the voltage level at the capacitor, which is represented by that liquid crystal cell. Or sometimes, so this is addressing exactly same or can be similar to the memory, but usually it works such a way that you use a serial link through which you send the voltages for the individual components of individual columns. Then you activate, send the frame signal and activate the first row, and it is copied to the individual pixels. And then you say, okay, I want to left this row selection passive, set up new values on the columns, and then advance to the next line. And this way you need to refresh and refresh, because there is the problem that there is some leakage, same as for the dynamic memory. But and the capacity of that liquid crystal cell is relatively small, so in this case we have there some additional capacitor storage provided to keep the value. In the case of OLED, organic LED display, it works relatively same way, but we have there capacitors which control only the resistance of some transistor which directly controls the intensity of the given LED. This is Vivado design system. We can see there the block diagram of our design. We can iterate over this design, and we can, for example, if we look, there should be somewhere some that SPI, yes. So basically we see the sources, and we can go down. Okay, so I can go down to the design, and if we go down to the SPI LEDs, then we can see how it works. SPI LEDs, it is here. Yes. And this way we can go to the actual source level. So this is the source of the hardware. So basically there we can find those individual wires which represent, those are subcomponents, but the actual start of the definition of the component, it is somewhere here, yes. So basically entity, SPI and encoder, and what you see here are those individual wires which represent that interface to the AXI bus. And you need to map them to some state automata which checks when data arrives and so on. But you do not need to take care about the individual wires on the interconnection level, because there you have the diagram, which I can try to take out. So if I go to the diagram, then we can see how it is connected. So basically, this block represents the processing system. So it represents the actual hard cores of the ARM and so on. We can look at the configuration of this block here, and set up the individual parameters. Those are those ports which GP ports. This is that master port and slave ports. And so this port allows to access the peripherals in FPGA, and those another ports allows to access the memory from the peripheral. So for example, you can build a peripheral which takes the data from the cameras and stores them to the memory. And there is the possibility to configure the peripherals and all that frequencies, clock, DDR memory, and so on. And then we get to this. Okay, I'm not sure if yes. To this port where we have that bus with the connection for the peripheral. So you see there all those signals and a lot of more of them which we have spoken about during the description of the AXI. But you connect it by the single wire this way through the design to the block which works as AXI interconnect switch. So you do not take care about individual wires because it is the thing of the tool. And if you want to go to those SPI LEDs, I think that it is, which signal it is? It is displays, this is display, and SPI LEDs are in this design, probably this wire. So this way we get to the description of the individual registers and so on. We can continue, we can configure this block and so on. So this way you can build your own system up to the, for example, solution where you have some coprocessor running in the FPGA, which supports some operations and so on. So this is all for the short introduction to our hardware.